Today we'll be trying to find the mass of a black hole using surprise, Newton's second law, and Newton's law of universal gravitation. So how will we do this? Well, first let's consider the equations that we're going to need. Here's the momentum principle, a derivation of Newton's second law, and Newton's law of universal gravitation. We're going to solve for Fnet using the components of the momentum principle and by analyzing the motion data from a star. Assuming that the black hole is the only object acting on our star, we can calculate m2 in Newton's law of universal gravitation, or the black hole's mass in this case. Instead of using paper and pen, we're going to use our very own VPython code to do the work for us. To initialize our data, we need to insert all the variables that are known to us, the star's mass and the black hole's position, which are given to us. Using these two variables and the data of the motion of our star, we can solve for the mass of our black hole. Notice that delta t is 1 day, or 86,400 seconds. This is appropriately small considering the scale of our model. This first while loop will take in the motion data of the star and calculate the velocity of the star using the star's position and time. The second while loop is where the majority of the work will be done. The loop will find the initial velocity and the final velocity of the star, as well as take that information and find the initial momentum and the final momentum by multiplying said velocities with the star's mass. Ultimately, all of this is to find delta v and delta p, which are found by subtracting the corresponding velocity and momentum initial values from the final values. dp dt is equal to the change in momentum over the change in time. And looking at our momentum principle, it states that dp dt is equal to the Fnet. This is really important, as this is how we will use Newton's law of gravitation to find the mass of the black hole. But for now, let's find the components of Fnet in order to be more accurate in our model. First, let's look at the parallel component. P hat is simply the direction, which is P initial over its magnitude. The magnitude of the parallel component is the magnitude of the final momentum minus the magnitude of the initial momentum over delta t. By multiplying it by its direction, P hat, we have the correct representation of the parallel component. The perpendicular component is found by manipulating the momentum principle to subtract the parallel component, which we just found from dp dt. And again, according to the almighty momentum principle, the perpendicular component of the change in momentum is equal to Fnet in the perpendicular direction. Now we have all the things necessary to find the mass of the black hole. Here's Newton's law of universal gravitation in code form. Again, notice that Fnet that we calculated earlier can be substituted into the force of gravity because we are assuming that the pull of the black hole is the only force acting on our star. By running this line through each iteration of the second while loop, we will find the mass of our black hole. Let's go ahead and run our program. And here we are. Notice that the arrows were largest closest to the black hole. The yellow arrow represented the Fnet, the blue arrow represented Fnet perpendicular, and the black arrow represented Fnet parallel. Our black hole mass was found to be 2.388 e to the 31 kilograms. Now the lab posed two questions. One was to discuss how Fnet and dp dt are different. According to the momentum principle, they are mathematically the same. However, each tells a different story. Aside from the differences in how they are calculated, Fnet tells of the total forces acting in the total, parallel, or perpendicular directions, while dp dt simply describes how the object moves in those directions. Here's the second question. What if? What if the black hole was replaced by another black hole at the same location and the motion of the star did not change? Would we be able to tell the difference? The answer is no. The way that we calculated the mass of a black hole banked on the motion of the star and the position of the star and the black hole's position. If these three variables stayed the same without more data or other forces acting on the star, we would not be able to tell the difference. Thanks guys for watching and have a great day.